Okay, so let's look at this rational function and let's try solve everything that comes with rational functions, or at least in a high school sense. Okay, so the first things first, a vertical asymptote. So vertical asymptotes just look at the behavior of functions, right, on your x and y axis. So it'll usually be this type of dashed line, right? So what's called an asymptote. Now to find your vertical asymptote, vertical is from bottom to top. Okay, that would be vertical. We can take the denominator of the fraction and set it to 0. And we can pretty much just solve. Okay, move forward to the opposite side. This becomes 2x minus 4. Divide both sides by 2, the coefficient of x. And I have x, in this case, which should be equal to negative 2. So my vertical asymptote is negative 2. So if I had to plot this on some function, I would go find negative 2 on my x-axis, which would be over here, negative 2. And we can draw our vertical asymptote. So what about a horizontal asymptote? Well, if this one's vertical, horizontal has to be this way. An easy way to remember horizon would be, let's say you're at a beach, okay? Because sometimes it's very difficult, or sometimes it's confusing, horizontal and vertical. Let's say you're at some beach and you see the horizon, right? Which is the sunset. You can look at the sunset. Now you can remember, well, the sunset sets over the horizon. So my vertical asymptote has to be sort of related to this idea. I don't really know how to explain it in an easier way than that, but it should give you a little bit of idea. And then vertical would just be the opposite. Okay, so how do we find the horizontal asymptote? Well, we can find the horizontal asymptote if these degrees or the exponents are both linear factors, which just means they just an x minus 2, simple expression. We can take the coefficients, the leading coefficients, and put them in a fraction form. So that means my horizontal asymptote is simply going to be 1 over 2. Note that x has to be to the same degree 2 times. So 1/2 would be over here. So let's draw our horizontal asymptote. Okay, when it comes to graphing these functions, we'll graph them step by step in another video. I just want to talk about this function. I will investigate all of these functions on Desmos after we're done, and then we'll see how these functions actually behave. But before we can actually graph this function, let's go find our x and y intercepts. Okay, so how do we find an x-intercept? Well, let's do y first. Let's find the y-intercept. It's a bit simpler. To find the y-intercept, I simply need to set x equal to 0. Okay, so my function is given as, my rational function is given as 2x plus 4. So I can substitute both my x's with 0. This gives me negative 2 over 4. Okay, negative 2 over 4, which can then be simplified to negative 1 over 2. So we have negative 1 over 2. So negative 1 over 2 is here. So my function has to cross this point. Okay, negative 1 over 2. So what about my x? Oh, excuse me, my y-intercept. Whoa, what am I doing? I was correct. So what about my x-intercept? Well, to find an x-intercept, I need to set my y equal to 0. So let's say we have y. Remember, f of x is just a reference to y. So let's say I have y is equal to x minus 2 over 2x plus 4. I'm going to set this equal to 0 to find my x-intercept. So 0 is equal to negative 2 over 2x plus 4. I can cross multiply 2x plus 4 multiply 0 is 0. So we're left with 0 is equal to 2 minus x. And then we can solve for x. So x is 2. So my x-intercept is going to be x is 2, which is over there. So now I can sort of draw my function, which will look something like that and something like that. Okay. So this is how we can solve. This is the mathematical calculations behind solving a rational function where you have a first degree and a first degree. Okay, first degree just means x to the power of 1. That's it. It's very simple. So let's move over to the next one. Well, in the next one, we have a first degree and a second degree. Now, what's interesting about this one is if your numerator has a lower degree than your denominator, my horizontal asymptote will be 0. Okay, so when you have a linear factor, this is what's known as a quadratic factor, to be honest. Let's write that. This is a quadratic factor. Okay, quadratic just means 2. Cubic factor is 3. Quadric factor is to the power of 4. And a linear factor is to the power of 1. Okay, so we have a quadratic factor of x to the second power plus 5x plus 6. In that case, this number is lower than this number. If that's the case, then we'll have y is equal to 0 for my horizontal asymptote. Okay. What about my vertical asymptote? Well, vertical asymptote, as we've learned just now, is just we just set the bottom, we just set this equal to 0, set to 0. That's it. So let's go solve this one. Let's set this equal to 0. I'm going to solve it over here. So we have x squared plus 5x plus 6 is equal to 0. I can use factorization to factor out two values. In this case, I have x plus 2 and x plus 3. Now I can solve for x. So x is going to be negative 2 and x is going to be negative 3. Okay, so I have my two horizontal or vertical asymptotes. In this case, it's going to be negative 2 and negative 3. So where can I find that on an x and y system? Well, I can find that in quadrant 2 and 3. This would be quadrant 2, this would be quadrant 3. So let's go find 2, negative 3. So I have this dashed line and our horizontal asymptote, which I'll do in red, is going to be somewhere there. So to find the x-intercept, let's find the y-intercept. The y-intercept, I just set x equal to 0, so I'm going to put it over here. The y-intercept, very simple. It's x minus 3 over x squared plus 5x plus 6. So y is equal to this. Now, if I set this equal to 0, it should be quite obvious that all my x's just simply cancel out, right? Because if we take 5 multiply 0, that gives me 0. If I take x squared, which is going to be 0 squared, that's also 0. And then 0 is 0. So to find my y-intercept, I can always take my constant over my second constant. Very simple. Just take your two constants. You might actually be given this form where you have ax plus b over cx squared plus dx plus e. So to find your y-intercept, in this case, all that we simply do is we cancel out these terms. So it's going to be, to find my y-intercept, I can say, well, x is 0, but I'm left with b over e. You might actually be asked to solve this question with variables, so this might be worth noting. Okay. Okay, so we found our y-intercept, negative 3 over 6. So we can say negative 3 over 6. That gives me negative 1 over 2 again. Okay, so my y-intercept is negative 1 over 2. It's over there. So we have 0. negative 1 over 2. Now what about my x-intercept? How do we find that one? Oh, the x-intercept, when your linear factor, remember, linear is 1. When your linear factor is above the line, it's very easy. You just move this one to the, you just solve, right? You can set the top equal to 0. Why? Because we create a 0 over here. We multiply this to the opposite side, cross multiplication, and we're left with x minus 3. So therefore, x is equal to 3. So my x-intercept is going to be x is equal to 3. And now, it's worth noting that your function will cross your horizontal asymptote. But as I mentioned in the beginning of the video, and I will investigate these two functions on Desmos to go a little bit into more detail, as I mentioned, is you only use the horizontal or the asymptotes to see the behavior of the end function. So you want to see where they end up. Okay, for instance, this one. When we look at this, we can see, well, this side is raising all the way to infinity. This side is going all the way to negative infinity. So we can see our y height is going to go to infinity, and our x on this side of the function is going to go to negative infinity. And then you can do the same thing here on the downside of the function, or the lower end of the function, and then the right side of the function. So we can see, well, this one's traveling to negative infinity and this one's traveling to positive infinity. But we'll get to all of this when we do the theoretical graphing of functions without calculators. Now it's worth noting all of this information. So the x-intercept, we said, is 3, 0. Okay, let's move over to this one. So what happens now? Now all of a sudden you have a linear factor at the bottom. So when you have a linear factor at the bottom, you actually don't have a horizontal asymptote. You have something that's known as an oblique asymptote. Okay, but we'll get to this in a second. So how do we find our vertical asymptote? Well, now the vertical asymptote is very easy to find. You just set the bottom equal to 0. Again, the same thing. It's all three examples. It's the exact same thing. To find the vertical asymptote, you simply set the bottom to 0. That's it. So my vertical asymptote is 2. Let's go plot this on a function, quick sticks. Just quick. Shapow. My x and y system, or coordinate plane, or coordinate graph, or system, collective systems, whatever you want to call it. Okay, I like to call it an x and a y system. Sometimes in physics this might be referred to as x1, x2, however, but anyway, doesn't matter. So let's go find 2. 2 is over here, between quadrant 1 and 4. This is quadrant 1 and 4. Very nice to familiarize yourself with these type of things, you know. Now, before we get to our oblique asymptote, because this one's the most trickiest, let's go solve for our x and our y intercept. I'm going to write my function a bit more down because I cannot really see. Okay. So to find my y-intercept, very simple. I cancel out all my x's. Now listen. Let me be honest. Okay. Don't go say that. You just cancel out all your x's, because that makes no sense. Mathematically, we cancel them out, but we need to say we're going to set our x equal to 0, and that makes it cancel out. So don't say that, okay? But that's the idea. So then we are left with, well, my x is 0. Remember, a y-intercept is just a point. What exactly is a y-intercept? I didn't even speak about that, sorry. So let's say we have some function like this. A y-intercept is a point of cross where my function crosses my x-axis at, my y-axis at x is equal to 0, because there's no left or right shift. And my x-intercept is my point that crosses my function on my x-axis. Very simple. So this one's the x-intercept, this one's the y-intercept. Very simple. Now we're left with negative 12 over negative 2. We can see this gives us 6. So my y-intercept is 6. Let's go find 6. 6 is over there. Okay, between quadrant 1 and 2. My x-intercept, however, my x-intercept is I'm going to solve the top side of the function. So in this case, I'm going to all of a sudden now have two x-intercepts. Okay, because I set my y equal to 0. Look at this. If I set my y equal to 0, this one cross multiplies again, or we can multiply it with the reciprocal. Doesn't really matter, it's the same thing. It just disappears, right? I don't want to make it complicated. Guys, it just disappeared. Look there. Boom, gone. Okay, that's it. So you can just set the top equal to 0 to find your x-intercepts. So now we can solve this one. We can say x minus 4, x plus 3. So therefore, x is going to be equal. You set this one now equal to 0, set this one equal to 0. So x sub 1 is going to be 4, and x sub 2 is going to be negative 3. So let's go find 4 and negative 3. So 4 is over here, and negative 3 is over there. So now we have these points. Now what about this oblique asymptote? Well, to solve an oblique asymptote, we're going to do this. We're going to actually perform synthetic division. So the idea to find your oblique asymptote would be to divide x minus 2 divided by this part, this quadratic function, this quadratic equation. Actual expression, quadratic expression, sorry. So how do we do that? Well, first things first. This is how you do synthetic division. Quick little video. Synthetic division. I have a video on this. This is within the rational zero theorem. I would highly recommend go watching it if you don't understand. But this is the idea. The idea is that you solve the bottom half of the fraction. You set equal to 0. So x minus 2 is equal to 0. Therefore, x is equal to 2. Then you're going to create this box. 2. So let's see. I'm going to write this out as it's written over there. Minus 1x minus 12. Now, all you simply do is you take these values in front of x. Look, you take these values in front of x and you place them in here, in this box. So 1 minus 12. So what we do next is you take this 2. Okay, wait. First, you bring this one down. You do nothing to this one. This one's is okay. It's okay. You don't do anything to it. Next, we're going to take 2 multiply 1. And we're going to write our answer over here. Then you add them downwards. So it's going to be negative 1 plus 2, which is 1. Then you have again 2 multiply this one is 2. And then we plus together, so we get negative 10. So you are left with, because you divide it with ax, you are taking away one of the x's. Currently, this is an x squared equation. Because you divide it by 1x, you're taking away an x. So now we can write this as a new equation. We can say, this is going to be the new coefficients of my equation. So it's simply going to be x plus 1. Now, in this case, we have a remainder. Okay, so since we have a remainder, we can simply just write this, and we can divide this by the original statement. The original statement was x minus 2. You can use synthetic division to find this oblique asymptote, or you can simply use long division. Okay, whichever one you prefer. It's up to you. You can do it. So what is the oblique asymptote? Well, the oblique asymptote is going to be this thing. Just this. Just that expression. We cut out the remainder. So throw it in the trash. No, I'm just kidding. We don't do that. So x plus 1. So now we can actually just quickly state a little function. Y is equal to x plus 1. Now we can go create our oblique asymptote. We have x plus 1 is my new asymptote. So if my asymptote is x plus 1, I start with my y-intercept when graphing a straight line. This is currently, you can think about this currently as a gradient intercept form or slope intercept form. Y is equal to mx plus c. It's the same thing. Or y is equal to mx plus b. Or if you really want to be special, you can even say y is equal to mx plus k. Whatever you want to do. Okay? I mean, if you want to be really special, you can say y is equal to delta y over delta xx. Just kidding. Anyway, so we start at 1. Now we have a slope of 1 over 1. So we go 1 up, 1 right. And there we go. Now we link this. And there's my oblique asymptote. And I will go plot this function as well on Desmos. And we can do a little bit of an investigation over there. But remember what I did here. Maybe I'll compare the two. So I'll share my screen in two. Okay. This question, what I did was, now guys, this is supposed to be a dashed line. Okay, this is just for educational purposes. Please understand that I'm using y is equal to 1/2 and x is equal to -2. It's only for educational purposes. It's supposed to be a dashed line. I mean, I can do this by saying maybe this one. Look at that. Wait, let's see. Can we actually say no? I'm going to just use an equal sign. But look, so these are the asymptotes we calculated, right? And we went to graph them. So look what happens. Even if I go up into infinity somewhat, these lines, it won't really cross. So we can sort of make a prediction how this function will behave by looking at my vertical asymptote of -2. We can see what happens to the function. Okay? For my horizontal asymptote, I can look at it and I can do the exact same thing. You can sort of test your asymptotes this way if you have technology in your exam. But when I zoom in, we can see, wow, 1/2, that's my vertical asymptote. So we can see how our function behaves in the second quadrant. Okay, I'm going to go back to home. So this is the first function I calculated. I'm going to input the second function, quick sticks. Calculated the two asymptotes. Remember, there were 2 asymptotes. So the reason there's now, guys, before I get to something, yeah, I will teach you guys how to, I mean, if you watch this video or whatever, or the next one, is we will learn how to graph these functions without a calculator. But for now, actually, that might be a little bit tricky. Anyway, so we said our vertical asymptote, our y, or horizontal asymptote was 0. So if I somehow zoom in here, we can sort of see that, well, this function really never crosses my asymptote. So we can see in the second quadrant, or that's in the third quadrant, is moving to infinity. And downwards, the first asymptote I calculated, the vertical one, was -3. So we calculated -3 and -2. If I look at the behavior of these functions to my asymptotes, we can see, well, hey, look at that. They sort of look parallel, even though they're really not, but they kind of look parallel. You know, parallel just means they never touch. So we can predict the behavior of this function. Now I'm going to go here. Look, we have our x-intercept, which we calculated. We have our y-intercept, which we also calculated. We have our 3 asymptotes that we calculated. But now all we need to do is input some values into my function that makes my function not undefined. So we sort of want to stop at -3 and -2. And we can use all the values from the right and all the values from the left of -3 and -2 if we want to manually plot this function. Now let's go look at the final one. Okay, so I decided to look at my maybe I take this part out. Anyway, so these are the points we calculated, right? We calculated this point, and this point. So let's look at this. -3, 4, and 6. Those are the points we calculated. This oblique asymptote, look at this. If you go up, we can now even predict the behavior of my function when it has a linear factor by a slope-intercept form graph or a diagonal graph. You know, how crazy is that? Look at this. If we zoom in, we can predict what's happening. What about the vertical asymptote that we found as 2? Well, we can look at these asymptotes, how they behave going upwards and how they going downwards. So this would be the idea behind calculating the asymptotes, right? It might seem kind of pointless and repetitive. Of course, we can simply find this one's quite nice, in point of intersection. So our asymptotes intersect here, which is man, I really hope I'm pronouncing that thing correct. Oblique. I used to call it something else in my country's mathematics. Yeah, I did study mathematics in a different language, but the English one is a lot easier. But I hope I'm not butchering the pronunciation. If I am, apologies, man. You know what I mean? Anyway, everyone, have a fantastic one. And this is the basics behind I mean, this is not basics, to be honest. It's like, maybe for high school, it's a little bit advanced. But you can do it. I know it. Anyway, goodbye.